Hill Climbing Applications and Simulated Annealing by Group C. Written by Manuel Umaña, Dahyna Martínez, Pérez, and Christopher Hens. Agenda: Purpose of the experiment, hypothesis, concepts, experiment setup, information, conclusion, credit, and reference. Purpose of experiment: study the performance of different hill climbing algorithms utilizing the different implementations. Study the performance of simulated annealing in two puzzles, the 8-puzzle problem and the 8-queen problem. Key questions and hypothesis. How effective are different approaches of hill climbing and annealing given the same problem? Are there a difference between the different subsections of the algorithm hill climbing? Is annealing better than hill climbing in all problem formulations? What is the efficiency of the different subsections of the hill climbing algorithm and annealing? Hypothesis: simulated annealing would fare better at solving the given test than hill climbing, as it is not constrained in only doing the most optimal move. Concepts: the experimental concepts were the platform Python and the subjects: steep ascent hill climbing, first choice hill climbing, random restart hill climbing, and simulated annealing. The 8-puzzle problem places 8 numbered tiles in a 3x3 grade in a specified order with the least amount of possible moves. The 8-queen problem places 8 queens in a chessboard, 1 for each column of the board, and you change the positions in such a way that no queen attacks each other directly under. The measures used were the Manhattan cubes to function and the attacking pairs used to function.
Experiment setup. Tools and resources utilized. The following tools and resources were used. I'm a code repository. The core repository contained fundamental code and algorithms for the problem. For problem 4.4, simulated annealing and subsets for the hill climbing algorithm were created using the base foundation of the I'm a code repository for the given problems being instances of 8-puzzle and 8-queen problems. The created subsets included steepest ascent, first choice, and random restart for hill climbing. Methods for comparing. The criteria used for comparisons were performance, if the algorithm found the optimal solution to the problem or how close it was to find the optimal solution, and what is the percentage of success. Efficiency evaluates the amount of moves it took to find the solution if it found it. In problem 4.4, the same criteria was used, adding to the fact that a direct comparison was made with the number of successful attempts against the failures. How the data for the graphs was collected and used. For exercise 4.4, the information was collected after the algorithm finished running. The collected data was compared with the goal state of the problem. The solution gathered, if found to be the same, was added to a success list that counted how many instances actually succeeded the problem. The cost is put in a scatter plot with the optimal cost as the x-axis and its actual cost as the y-axis. Information. These are the results of utilizing the steepest ascent hill climbing algorithm with 10 randomly generated puzzles. For this case, the problem was the 8-puzzle problem. Initially, the search cost was way bigger than the Manhattan distance, which was our optimal cost. This is noted by the second graph, where it is noted that none of the puzzles were able to be solved. Next, we have the 8-queen puzzle utilizing the steepest ascent hill climbing algorithm. Again, 10 random puzzles were generated. It is noted in the graph that the search cost and the Manhattan cost have very similar values. This can also be portrayed in the graph next to it, where only 30% of the puzzles were solvable compared to the last section where none of the problems were solvable.
These are the 10 instances for the first choice hill climbing exercise. Over here we see the results of the 8 puzzle for the 10 instances of the first choice hill climbing exercise. As can be seen, it was not able to be solved. Over here we see the 10 instances for the 8 queens puzzle utilizing first choice. In the results for the first choice hill climbing exercise, we can see that 20% of the puzzle instances were managed to be solved, with the optimal cost being around 3. Over here we see the 8 puzzle using random restarts, and we see the solutions for the 8 puzzle random restarts in that none of the instances were able to be solved. We see the 8 queen puzzle using random restarts for the 8 queens. Over here we see the biggest offset, being that the 8 queens puzzle was able to be solved about to a 90% using random restarts.
These are the results for the 8-puzzle problem using simulated annealing. Here you can see that none of the solution states are even close to finding the solution. These graphs show the search cost versus optimal cost and the percentage of solved and unsolved puzzles of the 8-puzzle problem using simulated annealing, showing a 0% of success rate. For the 8 queens puzzle using simulated annealing, there were 2 variations to consider. Figure 8 shows the results for the 8 queen puzzle using simulated annealing without initial state, this being the first variation used for this problem. This graph shows the search cost versus optimal cost and the percentage of solved and unsolved puzzles using simulated annealing without initial state, showing a 20% of success rate. Figure 9 shows the results for the 8-queen puzzle using simulated annealing with initial state, this being the second variation used for this problem. This graph shows the search cost versus optimal solution cost and the percentage of solved and unsolved puzzles using simulated annealing with initial state, showing 0% of success rate. Conclusion: hill climbing limitations. Hill climbing offers a fair amount of robustness as it always chooses a state that improves the current one. However, it has noticeable limitations that stop it from consistently finding the solution to a problem. Complexity and efficiency of alternate algorithms. Enhancing hill climbing with additional features improves effectiveness, but it increases complexity. The variants used for this project enhance heuristics but have drawbacks. Annealing expectancy. It is effective at solving complex problems, but inefficient for the problems studied in this project. The state space was discrete and small, which made it difficult for the algorithm to explore effectively. References.